Cashmore, and I've been working on encoding planning problems as quantified Boolean. Okay, encoding a planning problem as a SAT problem is quite a popular approach right now. The papers from Robinson 2009 and Winter 2006 are the current state-of-the-art approaches and have been shown to do really well on all sorts of different problems. In all approaches to encoding and planning as SAT at the moment, the problem is first grounded. It means taking the operators and binding the objects to create actions and the predicates to create facts. The plus side to this is that it makes very easy SAT encodings in which the variables of the SAT problem correspond directly to the parts of the plan, and it's very easy to extract the plan from them. The downside is the SAT problems can be much bigger than the original domain or problem descriptions. You end up with millions of clauses. So the idea here is to use quantified Boolean formula, which is piece-based complete, same as planning, in order to avoid grounding if something is put together. So this is just an example of SAT encoding, which is most similar to the partially bounded QBA encoding that we'll be introducing in a minute. So there's a variable for each ground fact and for each ground action, and this creates a set of variables which describes the state. And then you copy this set of variables and have a state for every time step, and then the constraints enforce that actions variables may be true in any set, imply that there are two conditions must be true in the same set. Any fact that is true in the set must be supported by an action variable in the previous set, or it must be itself true in the previous set. And then it's easy enough just to say, okay, we'll try 10 sets of these. Is there a plan with 10 time steps? And if no, iteratively deeper. We also include constraints for mutual exclusion relationships between actions, and to ensure that the initial state holds on the first time step and the goal is true in the last step. Alright. So quantified Boolean formula extends SAT to allow for universal quantification of variables. Preceding the formula itself, we end up with a quantification line in which all of the variables are quantified either existentially or universally in order. So, in the first example there, we would say there exists an assignment to the variables A and B, such that for every assignment to variable C, there exists an assignment to variable D, such that the formula is satisfied. If this were just a SAT formula, it would be satisfying. You could say that B is true, which will satisfy the last two clauses there, which means that A must be false to satisfy that first clause, and that leaves C to be true, and the formula will be satisfied. However, as a quantified Boolean formula problem, it's unsatisfying, because there is no satisfying assignment to A, B, and D for the case where C is false. Below here, this is satisfying, as the assignment to variable D can be different depending on the assignment to C. So for example, when C is true, D can also be true. And when C is false, D can be assigned false, and the formula is satisfied in both cases. So what this really means is that C is creating a branch, a binary branch in the structure of the problem, and D can have a different value in either of these branches. So, instead of grounding, what we're going to do is use each of these branches to describe a different instance of an object of the same type. So if we were to have a problem with a single type of object, we had 100 of them, we create an encoding very similar to the SAT one I described, in which we describe one type of this object. And when the universal variables are assigned, and we're down a single branch, we have the plan for one of these objects. Then a different assignment to these universal variables will describe a different object. Okay. So the first step is to use the idea of split operators so that we can get the types of objects separated for grounding and ungrounding. So, for example, here we take the operator unstack and we split it actually into 4 operators. The first 3 corresponding to the parameters, and the last one as a sort of placeholder operator that says we're unstacking this time step. And we also do the same with predicates. Okay, so our quantification then will look like this. We're saying that there exists the set of grounded variables, so that would be actions and facts, for each time step from time step 1 to time step n. And then we have a set of universal variables whose only purpose here is to create the branches that we need for grounding. And then we say that there exists a set of the ungrounded variables from time step 1 to time step n, and this will consist of the predicates and operators. We also include a set of variables to the grounded set corresponding to the parameters of the ungrounded operators. And we include sets of variables to the ungrounded set corresponding to the parameters of the predicates. I'll describe why in a second. Okay. So using the unstack example again, this is how we split operators and predicates will be placed. We have our placeholder unstack action is allowed 1 assignment, depending no matter what the universals are assigned. And then the rest of unstack is down here. So we only have 1 unstack 1 and 1 unstack 2 operator, but those will be given a different assignment for every action that we might be performed with that state. We also split the on predicate and stick that to the ungrounded. So that those 2 variables there represent the on fact for every block. Above we have the parameter variables for unstack 1 and unstack 2. Those are going to describe which block is being bound to this parameter here. So if, for example, the block represented in the branch of the universals for which all the universals are false is to be bound to this split operator, then all of those parameter variables will be constrained to also be false. These describe the parameter that's bound to the other part of the predicate. So for example, we're saying that block 1 is on block 2, then on 1, block 1 will be made true, and the parameter variables in this branch will be made to match the universals that describe the branch of the block that block 1 is on.
What do variable A1, AM represent? What do they represent?
So those are the universal variables.
Yes.
They represent nothing in the plan. They exist only to create 2 to the n branches. So if there were, if n was 1, we had a single universal variable, and you wanted to expand the QBF formula into a SAT formula, you would end up with a SAT formula that describes 2 sets of 2 copies of all of these variables, and so 2 blocks. So expanding all the universal variables until you had a SAT formula that created 2 PM blocks in essentially the grounding problem. So the constraints to this, as I said, actions will imply their preconditions, also operators will imply their preconditions, and facts and predicates imply disjunction of their supporting actions and operators and themselves in the previous state. And then we have these new conditions. We want to ensure that if we make one part of the split operator true, that all the other parts will also be true, and exactly one of each other will be true. We don't want to say, okay, we're going to unstack block 1 from block 2, and also unstack block 1 from blocks 3, 4, and 5. So that doesn't make any sense. We want to make sure that the parameter variables match the universals for a couple of reasons. The first is, in fact, to help with the first constraint, and the second is so that the effects of the action can be applied in the next state. And finally, we want to make sure that the parameter variables for the operator match the predicate values so that the preconditions are satisfied. So for example, if we are unstacking block 1 from block 2, and we decided that the parameter variables for unstack should be the branch corresponding to block 1 and block 2, then the predicate parameter variables for the on predicate must be block 2. As in, you can't unstack block 1 from block 2. Block 1 isn't actually on block 2. So here's an example of those. Okay, so the first one, we say that if any of these are made true, then unstack 0 must also be made true. This ensures that we don't perform only part of the action. Second, when the parameter variables for the split operator match the universal variables, then the corresponding split operator below must be made true. So when the universal variables have been assigned the value that corresponds to the block that's being unstacked, then the unstack operation must be made true if we are doing the action. And the third part, this is the precondition. If we are unstacking block 1, say, then the predicate on must obviously be true, and also the parameter for block 1 corresponding to the block that it's on must match the parameter, the second parameter of the unstack operation. Okay. So we implemented this and tried out in some simple problems which greatly benefit from a lifted approach. The first of which was just a very simple pigeonhole problem where we put pigeon in image calls. And we compared it against the example SAT encoding that I showed previously. And the encoding time was obviously much better since we were not really creating very many variables anymore. In this, both pigeons and pigeonholes were left ungrounded. And we were able to solve 2 more problems than was possible using the grounding approach within the 2-hour time limit per problem. And in fact, on this problem, the SAT approach ran out of memory before the 2-hour time limit was reached. Okay, this is the grip problem, which we took the first competition problem, just increased the number of balls. And the results aren't quite as good, but we are slightly faster. Okay, and then blocks were problems, which we increased the number of blocks and left the blocks ungrounded. And we were able to encode all of the problems and solve one more with the SAT approach within the time limit. Okay. So the next step is to compare with the more state-of-the-art SAT encodings. And one part of that is to experiment with different state representations in the partially grounded QPF encoding. So rather than encoding in a way similar to the example SAT represented, use these new SAT encodings to create a better partially grounded QPF encoding. Another thing to do is to put it in combination with other QPF encodings that we're currently working on, in which we reduce the number of time steps that we described. Okay. And crucial is that we get good results on some problems which benefit greatly from lifting. And on problems that have no good candidates for lifting, or very few candidates for lifting, our encoding will be just a SAT encoding of the domain. We wouldn't have any universal variables, and every variable will be grounded back to actual variables. So we don't lose anything from this technique. Is there any questions? Okay, thank you very much.
Yes. Which SAT and QPF solvers did you use in your evaluation?
I'll use Pico SAT, SAT solver, and Quantified Boolean QPF solver.
Also, just another short question. Are there problems you found, benchmarks that you found, for which a QPF encoding performs worse? Is that right?
Yeah. Problems for which there weren't really any good lifting candidates, such as motors, the QPF performed worse. This is due to the fact that the QPF solver is just nowhere near as good as SAT solvers. So generally, you'll only get better results than SAT solvers here if you've got a problem which is really good candidates for lifting, like rocks and equipment.
Yeah. Listen, I understand that SAT encodings may be huge, but I think that you do not have the same problem if you use CSP encodings, because it's possible to associate with SAT encodings. You associate a variable with each grounded action, but with CSP encoding, it's possible to associate one variable with each action on each of its parameters.
Yeah.
And so
that's in a sense.
It's a big difference.
That's in a sense not grounding in the same sort of way as this. However, in that case, you have a CSP problem to solve it rather than a Boolean formula, which may be more difficult. It's interesting to run some experiments just to compare the two approaches.
For example, if in the blocks the world, it's possible to associate a variable with each. You have only one action variable which represents the blocks, which is taken at a given step. That's all. Just one variable.
Okay.
One action variable.
For each operator?
Yes, in this case there is only one variable.
Okay.
But how large would your domain be? So the domain of...
Yes. The domain represents all the possible blocks.
And then there's a different formulation. I mean, we're looking at encodings with domains, with variables have domains of size 2, don't we? So I think everything Michael said is restricted to the fact that we're looking at those kinds of...
It's known that SAT encodings may be very huge.
Yeah. Yeah, so then you could use constraint
but
encodings instead, or planning, or
something else.
It's possible to get better encodings. But I think what we've been exploring is can we get better performance than SAT using QPF, so the same kind of logic-based formalism, but exploiting the expressiveness of QPF. Does that allow you to buy anything? And if so, how do you exploit that? What are the mechanisms you need to put in place, and are they feasible? So I think what we've demonstrated is that you can achieve a lifting of the problem representation by using the expressive power of QBF, which is interesting. That's not to say you couldn't also get a better performance than SAT by using a constraint representation. That's certainly true. But we're exploring something a little bit different.
But QBF are mainly used in planning for non-deterministic planning.
Up to now, yeah. But
Yes.
we're saying
Yes.
you could use them for other things too, like lifted planning that's deterministic. So you're right, up to now that's been the focus, but we're trying something different.
Some more questions? No? Okay, thank you very much. Okay, then